Hey, mathematicians. We're going to be talking about symmetry today. It's not an entirely new concept to you. You've talked about it before. So we're going to talk about it a little bit more, extend on it a little bit, and then give you some time to practice. So line symmetry, all right, is where you can draw a line through any figure and it'll be the same on both sides, all right? Remember doing this when you were younger with the alphabet? You had to write all the letters out, I'm guessing, and then you drew your lines of symmetry and found out what letters had symmetry, what letters didn't, the H, the T, the A, the B, the C, the D, the E, but not the F, right? So which ones had line symmetry? And that line is known as the line of symmetry. That's the figure can be mapped on itself by a reflection in a line. That's called the line of symmetry. So when we're looking at figures and we want to figure out if they have line symmetry, we just kind of take a look and, for example, like this one really doesn't have a line of symmetry because if I fold it over, it doesn't work. So this nice little parallelogram doesn't have it. I would argue that this one doesn't have line symmetry based on the designs. If it was solid orange, for sure it would. But because it has all these little different designs in here, it's not going to have any line symmetry. This figure up here on the left, this one's going to have some line symmetry. Let me see if I can pull it over a little bit. There we go. All right, so it's going to have some line symmetry all the way through. How many line symmetries does it have? Let's figure that out here. Here. Well, how many is it? Let's count this out. And I always have to somehow designate it. So 1, 2, 3, 4, 5, 6, 7. 7 lines of symmetry. And this one, I would argue this one has symmetry too. I've had some students in the past be like, well, Ms. Shopper, look at right here. That's only a single line. But everywhere else is a double line. So it really only has one line of symmetry. Which I could take, like if you're going to get really super specific in your detail, I'm not going to argue with that. All right. So it really just has one. So just paying attention to that. So that's your line of symmetry. The other piece is rotational symmetry. Okay. That's when you turn it. Think of a dial. All right. So, it can be mapped on itself anywhere from 0 to 360 degrees. And it just depends on the figure. Sometimes it has, it's 180 and 360. Sometimes it's like in this example, 45, 90, 135, and so on. So just different numbers. So the center of rotation is your point of symmetry. That's going to be this dot right here. So like the center of it, how you spin it. Think of the spinner in life, or think of like if you have a gas stove when you turn your knobs, right? Like where is it centering on? So just a couple new vocab words: order of symmetry and magnitude of symmetry. So the order of symmetry is the number of times a figure maps onto itself as it rotates. So for example, a square would be 4 because it does 90, 180, 270, 360. The magnitude of symmetry is the angle of rotation. All right. So if I say that a square has 4, I can flip it 90, 180, 270, and then 360. The magnitude says I take 360 divided by 4. Each of those turns are 90. All right. So I do want you to make sure, because I'll ask you magnitude. Oops. I'll ask you magnitude and I'll ask you order. So just making sure you're understanding order is the number of times you can spin it from 0 to 360. And then magnitude is 360 divided by that order. That's the number of degrees to the first turn. All right. So do these have rotational symmetry? Yes or no? If they do, let's find the center of symmetry and state the order. So when I look at these, this one for sure has rotational symmetry. The star does. All right. So I can rotate it 1, 2, 3, 4, 5 times. So the order is 5, and the magnitude is going to be 360 divided by 5. So when I take 360 divided by 5, I get 72 degrees, right? When I look at the second one, I would argue that this one also has rotational symmetry. 1, 2, 3 times. So my order is 3. That gives me a magnitude of 120. So 360 divided by 3 is 120. All right, let's look at this last one. I've got 1, 2, 3, 4, 5, 6, 7, 8. 8. The order is 8 because it's 8 different stops. So that means the magnitude is going to be 45. All right. So difference between magnitude and order, rotational symmetry. And the last one we're going to talk about is three-dimensional plane and axis symmetry. So think about, the Earth, right? It rotates on its axis. Or you could think about the equator. And then if I slice the Earth that way, that's going to be plane symmetry. All right. So those are the two different types of three-dimensional symmetries we'll talk through. The axis when you're rotating, or like a top when you kind of look at it, or a dreidel would be an example. So those are different axis symmetries. And then plane, you cut a piece of cake, or you, what else? You take a can and you cut it, a box, that's plane symmetry. So we have to state whether these have plane symmetry, axis of symmetry, or both. This one I would say has plane symmetry because I can cut it, right like this. I can cut it down the middle that way. This one, like we had just talked, it's got plane symmetry with the great circle. And then it also has axis. So it's through the center, just kind of like the Earth. And I would argue that this one has only rotational symmetry, or axis of symmetry. Right. All right. You have time to work on your assignment. Score it and submit it. And then we'll chat soon. Take care, y'all. Bye.